Hello everyone and welcome to chapter number 3, video number 2 in the 3-phase induction machine course. In this video we are going to cover the torque speed characteristics. As you know, in the previous video we covered the power flow diagram, so now it's time to know how to calculate the motor torque. From the concepts we had before, to calculate the torque equals power over omega. So let us call back the power flow diagram of the 3-phase induction motor. We have input power, we have stator loss, we have air gap power, rotor copper loss, developed power, rotational loss, and output power. So output power, we can call it output useful net shaft or even brake horsepower. So 1 horsepower equals 746 watt. So to calculate the torque at the shaft, or net torque, useful torque, shaft torque, equals power output P net, P useful, P shaft over omega R. Omega R equals 2 pi NR over 60. So we need to know the rotor speed. Also we have torque lost due to friction. So that one will be the power rotational loss over omega R. If we add net torque to the lost torque, we have the developed torque, which will be produced inside the motor, equals P developed over omega R. But let me remind you that P developed equals P gap 1 minus S, and omega R equals omega S 1 minus S. So if we substitute by P developed and omega R from these two equations, so we are going to end up that torque developed equals P gap over omega S. So developed torque inside the machine equals P gap over omega S, and at the same time equals P developed over omega R. These two equations are equal. But that one is different from the net torque because there is a torque lost due to friction here in this area. So we are going to start from this equation to look for the torque speed characteristics. So developed torque equals P gap over omega S. So we are going to substitute from the power flow diagram about P gap. Torque developed equals 3I rotor square R rotor over S omega S. So we substitute by P gap equals 3I rotor square R rotor over S. From the approximate equivalent circuit or second approximate equivalent circuit we are going to use here, we need to calculate I rotor. So I rotor equals V phase over Z equivalent. So I rotor as a magnitude equals V phase or V supply phase value over root R stator plus R rotor over S square plus X equivalent square. So we are going to substitute by this equation here, and then we are going to find the torque developed. So the torque developed equals 3 V supply square or V phase square R rotor over S omega S, RS plus R rotor square plus X equivalent square. So if we notice here, the torque is function of the slip, where S is function of the speed. So the torque is function of speed, NR, of the motor. So we can plot torque speed characteristics or torque slip characteristics. Before we plot the torque speed characteristics, I'm going to explain something quickly here. Assume we have a pen like this one. Are you sure that we are in the 3-phase induction machine course? Yes, I deliberately put this slide. So if we have a pen like this one, and we have something like this chair, and we have something funny here like this elephant, so we can say that this pen is too small compared to this chair, and the chair is too small compared to this elephant. Or from the other side, the elephant is too big with respect to the chair, and the chair is too big with respect to the pen. So one time we look for the chair as too big, and one time we look for the chair as too small. So here we are going to use the same concept for the slip term. One time the slip will be too high value, and another time will be too low value. So this is how I'm going to give you the idea. So why I'm going to choose the slip term S. One time will be too low, and one time will be too high. So now back to the torque equation. Torque developed equals 3V phase square or V supply square R rotor over S omega S RS plus R rotor over S square plus X equivalent square. So the range of the slip is from 0 lower than S lower than 1. If S close to 0, this means S is too small. If S close to 1, so S value is too high. So we are going to start by if S is a high value, so S close to 1. If S close to 1, this means R rotor over S value will be small enough with respect to R stator, so we can cancel this one with respect to R stator. So if we look here for this equation, if we cancel R rotor over S with respect to R stator, so in this case, that one will be a constant, that one will be a constant value now, that one will be constant value, so torque equals K over S, or we can say that torque is proportional to 1 over S. So we have this inverse function. As S close to 1, so we have this inverse function as we can see here. But if S is close to 0, so this means this term will be too high compared to RS, and RS can be neglected with respect to that one. So that one will be R rotor square over S square. We can take that one, put it here, cancel one of the S's with one of this S square. So in this case, torque equals Ks, which is linear function. So torque is proportional to S. So we have two functions now for the torque equation. One when S is too small, which is like linear function here, and another one when S is too high, something like inverse function. So how in one equation you can accommodate two functions? Let's sketch the torque slip characteristics when the slip varies from 0 to 1. We have two relations in one equation. When slip tends to 0, torque is proportional to S. When slip tends to 1, torque is proportional to 1 over S. So how we are going to plot the torque equation to accommodate both relations? So definitely we have two asymptotes here. So when we have two asymptotes like these ones, we have a maximum point or maxima. This is the maximum torque we have. So the curve is varying from 0 to 1 and passing by a maximum point. If we look for the horizontal axis, it varies from 0 to 1. This means NR equals NS when S equals 0. So NR is the rotor speed, NS is the synchronous speed. And when S equals 1, NR equals 0. What do you think if we flip the horizontal axis or change S rather than to be from 0 to 1 to be from 1 to 0? Let's look. When we change the horizontal axis from 1 to 0, this means the horizontal axis varies from 0 to synchronous speed. So that one is the direction of increasing the speed, from 0 up to the synchronous speed. And that one is the direction of increasing the torque. And definitely when we have S equals 1, we have a starting point here. And we have here a maximum torque at specific point or specific slip. So there is another question. What will be the case if the slip is lower than 0 or more than 1? So the motoring action will be from 0 lower than S lower than 1. Lower than 0, that one will be a generator action, and more than 1, that one will be a plugging mode. So that one will be a braking or plugging mode. So we are concerned here by this course for motoring action. Generator and plugging mode will be another course or advanced course. Let's delve more in these torque speed characteristics and ask ourselves a question. Which point the motor will operate in stable operation? Q1, Q2, Q3, or Q4? We know the relation between power and torque and omega, where power equals torque omega. So if the speed increases, the torque should decrease for constant power operation, and vice versa. If the speed increases, torque should decrease. So let's look for this table now. We have at point Q1, we have speed nr1 and torque T1. At point Q2, we have speed nr2 and torque T2. At point Q3, we have speed nr3 and torque T2. At point Q4, we have speed nr4 and torque T1. Please note, nr1 is lower than nr2, nr3 is lower than nr4, and torque 1 is lower than torque 2. So let's examine the points Q1 and Q2 if the motor is going to move from point Q1 to Q2. From Q1 to Q2, the speed increases and the torque increases as well. So now let's examine from 3 to 4. So the motor is moving from Q3 to Q4. From Q3 to Q4, the speed increases as well, but the torque decreases. So this means points 3 and 4 are stable, while 1 and 2 are not stable. If the motor is moving from 2 to 1, speed decreases and torque decreases. If the motor is going to move from 4 to 3, speed decreases but torque increases. So this region represents stability and this region represents unstable mode. So let's look here. The shaded area is a stable operation for the motor, and we have a stable region, and before the maximum point we have unstable region. So the maximum torque separate the motor torque speed characteristics into two regions. One of them is unstable region and another one is a stable region. So we can say that from S 0 lower than S maximum, that one is a stable region, while from S maximum is smaller than S smaller than 1, that one is unstable region. So now we can put the torque speed characteristics in the final format. We have here two regions, one before the maximum and another one after the maximum, which is a stable operation. So the motor is going to operate in this region. That one is the stable region. So we have here a starting torque. We have a maximum torque at specific slip. We call it S maximum torque. So the motor can operate at a point like this one is called developed torque at specific speed and specific slip. So I need to identify something here or clarify something here, that the red color is the motor torque speed characteristics, while the blue line is the mechanical load characteristics. And the motor will operate when we have a point matches both the motor torque speed characteristics and the load torque speed characteristics. So that one something like a fan or a compressor. So the motor is going to intersect at this point. So the motor is going to deliver a torque with certain speed to satisfy the mechanical load requirements. So analytically, how to calculate different torque points? We are going to start by the starting torque. So we have the equivalent circuit. I'm using here second approximate equivalent circuit because I'm focusing on the rotor side. So R stator plus R rotor over S. But at starting, the rotor speed is 0 and S equals 1. And we call that one at standstill or at starting. So we are going to calculate the starting torque and starting current at this point. So we are going to substitute in the equation to calculate the rotor current at starting, where the rotor current at starting will be R rotor over 1. So once you know I starting, you are going to substitute in the torque equation, where the torque equation will be 3V phase square R rotor over S, which is 1 omega S, R stator plus R rotor over 1 square plus X equivalent square. This is one of the methods how to calculate the starting torque, but some students like to calculate it by another way, that they calculate I starting and then they calculate B gap at starting, which is 3I starting square R rotor over S, which is 1. Right? So that one as starting. At starting, all the air gap power is consumed as rotor copper loss. So once you have this one, you are going to substitute in the torque equation, where the torque at starting equals B gap over omega S. So what is the role of R stator? To calculate starting current as well will be included in the starting current equation. What about the maximum torque, or we call it pull-out torque? So the torque equation we know is torque developed equals 3V phase square, or V supply square but phase value, multiplied by R rotor over S omega S multiplied by R stator plus R rotor over S square plus X equivalent square. So the equivalent circuit, as we can see here, I'm using second approximate equivalent circuit, and I have here the torque speed characteristic. I'm concerned by the point here, T maximum at specific S maximum. So the equivalent circuit will be R rotor over S maximum. The question now, how to calculate S maximum? So the torque is function of the slip S. So from math, if we differentiate the torque equation with respect to S and equals that one to 0, we are going to find S, which equals S maximum, and then we are going to substitute in the torque equation to find the maximum torque. That one is a long story. There is another derivation which is simple derivation. We know from the circuit analysis, if we have a load like this one, that one is a load, and we can represent that one something like Z Thevenin, and that one is V Thevenin. So this load takes maximum power if we have Z load equals Z Thevenin conjugate. Please return back to the circuit analysis theory. So for Thevenin equivalent, if you like to transfer maximum power to the load in DC circuit analysis, R load equal R Thevenin. But in AC circuit analysis, Z load equals Z Thevenin conjugate. So what will be the case if your load is pure resistance, something like boiler, for example? So in this case, we have the load resistance should equal root R Thevenin square plus X equivalent X Thevenin square. So in this case, to have maximum power transferred to R rotor over S maximum, so R rotor over S maximum should equal root R stator square plus X equivalent square. As if we have Z7 in here, R stator and X equivalent. So why you do that one? When we maximize the power going to R rotor over S maximum, this means we maximize the air gap power. When we maximize the air gap power, we maximize the developed torque. So at that time, we can calculate S maximum, which equals R rotor over this root. So let's look here. To find the slip, we can differentiate the torque equation and find the operator S when equals to 0, and then we're going to substitute in the torque, or using maximum air gap power transfer concept, like what I did here. When you do that one, you are going to find that S maximum equals R rotor over root R stator square plus X equivalent square. Take this expression and substitute here. You are going to find that T maximum equals 3V supply square over 2 omega S RS plus root RS square plus X equivalent square. Another one said that I'm not going to memorize these equations. Simply you are going to calculate S maximum, then you are going to calculate I at S maximum, and then you are going to calculate B gap at maximum, and then you are going to find torque maximum equals B gap over omega S. So once you have that one, you're going to find the torque. So either you're using this equation directly, T maximum equals, or work the step by step. I like to work the step by step. Calculate the current at S maximum, power gap at S maximum, then torque maximum. If RS is neglected with respect to X equivalent, so S maximum equals R rotor over X equivalent directly. And in this case, torque will be 3V supply square over 2 omega S X equivalent. So the maximum torque will be function of the voltage square and the motor reactance. Let us continue with this assumption if the stator resistance is neglected, which is valid assumption in some cases. So torque developed will be 3V phase square R rotor over S omega S R rotor over S square plus X equivalent square. But from the previous slide, the maximum torque is 3V phase square over 2 omega S X equivalent. So we can find the relation between the torque of the machine at any point and the maximum torque. So torque developed over torque maximum equals 2SS maximum over S square plus S maximum square. And that one, or this expression, is valid only if the stator resistance is neglected. And also you can find the relation between starting torque and maximum torque if you put S equals 1. So in this case, torque starting with respect to torque maximum will be 2S maximum over 1 plus S maximum square. And that one is only valid if the stator resistance is neglected. Let's look deeply for the S maximum and torque maximum when the stator resistance is neglected. So S maximum equals R rotor over X equivalent, and torque maximum equals 3V phase square over 2 omega S X equivalent. So the torque speed characteristics, as we can see here, at a specific R rotor, so we have S maximum, and we calculated T maximum here at certain S maximum. Anyone notice something with the torque equation? So I noticed here that the maximum torque does not depend on the rotor resistance, while the position of the maximum torque depends on the rotor resistance. So S maximum is function of rotor resistance, but T maximum is not function of the rotor resistance. So what that means, I can move this curve to have the same maximum at different speeds if I change rotor resistance. So the maximum torque does not depend on the rotor resistance, but the slip for maximum torque depends on the rotor resistance. So if we add external resistance to the rotor resistance, we can move that curve and have the same maximum at different speed. So if external resistance is added to the rotor, S maximum equals R rotor plus R external over X equivalent. So we have at different speed the same maximum. At the same time, you are going to increase the starting torque. And that one is applicable only for slip ring induction motor. It's not accepted for squirrel cage because we cannot access the rotor in the squirrel cage motor. More, we can add another resistance to achieve the maximum torque at starting. So if we add another resistance, we can have maximum torque at starting. And at starting, S equals 1. So S maximum equals 1 equals R rotor plus R external over X equivalent. So you are going to calculate this external resistance, which satisfies maximum torque at starting. So you need to design that one in terms of rating and power capability. In this video, we derive the torque speed characteristics of the three-phase induction motor and how to find the torque analytically, and the main points of these torque speed characteristics such as starting torque and maximum torque. And what is the relation between the developed torque and maximum torque, starting torque and maximum torque when our stator is neglected. So what will I watch in video number 3? In video number 3, we are going to solve examples on power and torque calculation. See you in the next video.